This slide set is about fragmentation of IPv4 packets, which is a core feature of the Internet Protocol. If a system wants to send an IP packet, it has to provide it to the data link layer. So this is what we have learned from the OSI model or hybrid model. On the data link layer, there is a size limitation for the payload, which is specified in a technology-dependent manner. For instance, Ethernet 2 specifies this so-called maximum transmission unit as 1500 bytes. However, IP packets can be larger than this, because the IP header length field even allows sizes larger than 65,000 bytes. This size problem can occur on the original source of an IP packet, but also on routers in the network. Here an example is given where a router has to cope with different MTU values on different interfaces. On this slide we see an illustration how fragmentation, which is the method to deal with this issue, works. In the figure, IP packets are shown with a blue header and a green payload. On the first router in the ISPA network, the size limitation is exceeded. Therefore, the IP packet is split up and put into two different data link layer frames. This split up makes it necessary to have an IP header in each fragment, because control data is needed for the further forwarding of the fragments and to reverse the fragmentation later. In the drawing we see that an additional fragmentation happens for using the link between ISPA and ISPB. The reassembly only happens at the final destination. Now we take a look at fields in the IPv4 header and how they are used for fragmentation management. The flag field is composed of 3 bits. Bit 0 is not relevant. It always contains the value 0. The next bit indicates whether fragmentation is allowed. If the bit is 0, then fragmentation can be done as described. If the value is 1, then fragmentation is not allowed. The impact is that if fragmentation was necessary, it would not happen. Instead, the packet would be dropped and an ICMP error message, packet too big, would be sent back to the sender. IPv6 only knows this option and only allows fragmentation on the source, but not on routers inside the network. The last flag bit indicates whether a fragment is the last fragment or not. If it is set to 1, more fragments will follow. If it is 0, then it is the last fragment. If the IP packet is not fragmented at all, then the value is also 0. The next field in the IP header is the fragment offset. It indicates how many payload bytes have been part of previous fragments. On this slide we see a fragmentation example. The original IP packet has a size of 4000 bytes, that is, a header size of 20 bytes and 3980 bytes payload. Now fragmentation is necessary because an MTU size of 1500 bytes holds for the next link. As a result, there are 3 fragments. To recognize later that the fragments belong together, an additional IP header field is needed, which has not been mentioned before. The identification field has the same value for all fragments, but has different values for other IP packets. In addition, you can observe the use of the more fragments flag, which is called flag 2 here, and the fragment offset. The example is continued on the following slide. The fragments now reach another router where the MTU size on the outgoing interface is 1000 bytes. As a consequence, the fragments have to be fragmented again. As explained before, this happens for each fragment on its own, so that no reassembly is done on the router. The result is that each fragment is split up into 2 smaller fragments, so that there are 6 fragments at the end. In each fragment an IP header is needed. You can also see that only in the very last fragment the flag 2 is set to 0.